Okay, so you can see here a picture of Rainier Gamma Swirl with some image of CubeSat probes about to enter near the swirl. One major thing I want to get across in this talk is that swirls are not just interesting geologic features because they look very interesting, but they're actually at the intersection of many fields in planetary science, and I think that a mission to lunar swirls, a dedicated lunar mission to swirls, would actually inform a number of problems in planetary science. So not only going to tell you about swirls and some theories about how they form, but I'm also going to tell you about a very low-cost and realistic mission concept that UC Santa Cruz and UC Berkeley have conceived of and have been working on with NASA Ames small spacecraft office over the last 12 months. And this would be the first CubeSat mission beyond the Earth. Okay, so actually there's a really old investigation for lunar magnetic fields, which swirls are intimately related to. Actually, one of the very first objects to leave the Earth and approach the Moon was Luna 1, and it carried with it not a camera, but actually a magnetometer, among other things, and it was able to measure that the Moon doesn't have a global dipole field like the Earth's, and that was consistent with the idea that the Moon never really was, probably at the time they thought, ever able to attain a dynamo in its core, like the Earth's. Then later on, Apollo 15 and 16 sub-satellites were sent into nearly equatorial orbits and at much lower altitudes than Luna 1, and they were able to make these maps of magnetic field strength, and you can see this contour map of the magnetic field strength, and what emerges are some spots that are actually show very strong localized magnetic fields, implying that there's some material in the crust that was strongly magnetized. So this then said, people thought maybe, okay, maybe there was at some time in lunar past a dynamo, so it's ambiguous though. Maybe there's other processes that cause these anomalies. You can see here, that's, let's see, that's the anomaly I'm talking about. So today, though, we have a global map of the magnetic field. So you can see here, this is lunar prospector data at 30 kilometers altitude. You can see there's no pattern to the magnetization in the Moon's crust. It consists mainly of scattered anomalies. Rainier Gamma here, you can see this is a very prominent swirl location. And actually, amazingly, we don't know the origin of these magnetic anomalies. They may be related to perhaps impact processes. Impacts can generate plasmas, and these plasmas may have with them magnetic fields. Or they may be related to an ancient dynamo now extinct on the Moon, which is maybe more interesting to geophysicists. But I should also say we only have measurements of the magnetic field strength above 16 kilometers altitude. So the Apollo surface packages left instruments that measured magnetic field strength at the surface, but at these very interesting anomalies, we only have measurements from greater than 16 kilometers. Okay, so then what are swirls? I think swirls are one of the most enigmatic geologic features in the solar system. They are sinuous albedo markings, and they're correlated with magnetic fields. So it's an optical surface phenomenon correlated with strong magnetic fields. They have no obvious topography at the tens of meter level. And I'm going to show you that these objects are at the intersection of many fields in planetary science. And you can see here a map of the magnetic field strength and the contour over Rainier Gamma Swirl, which has become kind of the type example. And you can see it's the highest contours are associated with the strongest albedo anomalies at the swirl. This is from David Blewett, who's worked on swirls for some time now. Basically, there's two theories for how these interesting features form. Okay, well, let's see. Before I do that, I'll give you some other examples. Here's a close-up of Rainier Gamma. You can see it's obviously very interesting, lots of swirl-like qualities to it. This is like kind of this eye-like feature. They all have like structure at the 10 kilometer scale, but also finer structure down to 1 kilometer. Here's another swirl at Mare Ingeni, also very interesting feature. They're not limited to Mare locations, however, they're also they appear in the highlands. So here's another swirl near Airy crater. So again, obviously very interesting looking features. So one of the most well-known theories for how these things form is that the solar wind, okay, nominally the solar wind impacts a silicate object in vacuum, and it acts as a darkening agent, or it's space weathering agent, so it darkens surfaces. But at these features, we have magnetic fields. And just like Earth's magnetopause, it may be that these weak magnetic fields keep the solar wind from reaching the surface. And since the solar wind can't reach the surface locally, or is at least deflected away, the surface doesn't darken, so you get these interesting looking bright features. So that's a really clever, elegant theory. One thing that people have been bothered by is that micrometeoroids are also darkening agents. And micrometeoroids are not impeded by the magnetic field, so they should darken the swirl after billions of years if they're getting through the magnetic field. So motivated partly by that problem, I came up with another idea at Brown University, and that maybe actually, just like we heard in the earlier talk, dust is involved in this process. I don't need to review this too much. Charged dust lofting has been inferred since Surveyor. We don't have any conclusions yet on how it operates, but there's definitely some indication that it operates during terminator crossings. And so you have this dust that's lofted at the terminator crossing, and that lofted dust is charged, okay? So what's also interesting is that at swirls, you may have weak electric fields that exist locally. And those weak electric local fields maybe can push that levitated dust around. Okay, so how do you get electric fields at swirls? It turns out as the solar wind plasma encounters the magnetic field at swirls, there's differential separation of these heavy protons and electrons due to their different masses. And that differential separation can set up weak electric fields. So essentially, you get this charge separation electric field. And if you have this weak electric field, maybe you can push around. Negative dust may be attracted to this positive charge that gets set up, and maybe positively charged dust gets repelled away. Oh. I didn't do that, right? Okay. So anyway, so you can see here that if there's a weak electric field at a swirl, which is associated with this magnetic field, you can move dust around horizontally, potentially. And you can calculate how far that dust can move if you make some basic assumptions. So you can calculate the distance a grain travels here on the vertical axis compared to a weak horizontal electric field. And you can calculate how far that dust will move around for different lofting times. Maybe the dust is up there for 10 minutes, maybe it's up there for 1 second. And you can assume a 10 micron grain, and you can calculate the charge based on capacitance times voltage. And you can just see, you can plot these, make these lines for how far the dust goes. So for example, if dust is only lofted for 1 second, and we let 100,000 years go by, that's the time I'm using here, and there's an electric field of unity, say, then the distance traveled will be about the typical swirl length scale. And the interesting thing is that, so we actually have some measurements of the electric fields at weak magnetic anomalies on the moon from the Apollo program, and you can see that they fall in this range here. So in this range of weak electric fields at magnetic anomalies from the Apollo measurements on the surface, you can see that for 6-second lofting times, for example, after 100,000 years, a 10 micron grain can get pushed around the length scale you see at swirls. So it's plausible maybe that dust is actually an agent is being moved around at swirls. And interestingly, fine dust at swirls is the most easily moved around because it has the lowest mass. And fine dust is also the brightest fraction of the soil. So that's the other hypothesis that's operating here. So we have this dust idea and we have this solar wind idea, and they're totally different ideas, but both are very rich in their implications. The problem with the dust thing is the spectral, we should be able to test this by looking at the spectral properties of swirls. And are the properties, the spectral properties of fine dust, consistent with the spectral properties we observe? And actually, m cubed is going to be critical in helping us to understand this. So taking that point, I'm going to show you how swirls are actually this nice laboratory for understanding the broader field of space weathering and the interpretation of spectra from airless silicate bodies. So application one here is that these swirls are actually space weathering laboratories. So remember I told you space weathering consists of solar wind protons and micrometeoroids darkening the surface. You can see here the effects of that in a laboratory. This is a eucrite meteorite before irradiation, the reflectance versus wavelength. You can see this eucrite has this nice broad absorption feature. After you irradiate this sample, though, you can see that nice absorption feature disappears. And that's a problem for people that are interpreting the spectra of airless bodies. So this complicates asteroid interpretation, Mercury's spectra, and also the moon. And one of the most fundamental things is we like to understand what is the solar wind doing versus micrometeoroids, because both of these are supposedly agents of space weathering and the destruction of these nice absorption bands. So to illustrate that, I can also show you some spectral observations at swirls. So basically, what people do in the area of space weathering, if you look at the moon, you can plot the ratio of 950 versus 750 nanometer reflectance versus 750 nanometer reflectance for a very boring area of the moon. Just say this is nearby a swirl in the mare, and you'll see that over here, this is very dark. It's very low in 750 nanometer reflectance. This is mature, old, space weathered soil, but somewhere in there, you're mixed in some immature craters, and these are brighter, and they form this linear plot in this space. So that's a normal kind of space weathering trend that we see on the moon. But what's really cool about swirls, okay, if you look at swirls and you take, for example, this the pixels in this black area, this is a swirl near Rainer Gamma, and the pixels in this black area form a trend that is displaced and downward over here. That has the same slope, but it's just offset. So you get these new trends within swirls, and this is something we don't really understand or observe anywhere else. So swirls are doing something to our nominal space weathering trend. Okay, and one interesting interpretation may be that we're actually seeing the difference between micrometeoroid and solar wind weathering. So maybe the micrometeoroids create this kind of trend here, and the solar wind flux as you move into or out of the swirl. So for example, these black pixels here, these black rectangle here inside the swirl, maybe these pixels here are actually the area where the solar wind flux is most stood off. So this could be a really nice lab for understanding this process. Okay, so I hope that application to the space weathering community is obvious. There's another application that's to lunar water, actually. So this is a more recent result. So lunar water on the moon. So actually this, you can see this is a figure from Cover of Science, Peters 2009. It shows that the poles of the moon have more hydroxyl molecules than near the equator. Interestingly enough, from this paper by Georgiana Kramer in JGR, it's coming out soon, you can see that actually the brightest parts of the swirl are depleted in hydroxyls relative to their surroundings. So maybe this supports the idea that the solar wind isn't reaching the surface there and it's not able to create these hydroxyls. So she's going to be talking about this Thursday at 8:55 a.m., I believe. So that's a really interesting new result for lunar swirls. So basically, if we study Rainer Gamma, Rainer Gamma swirl, this could give us insight into how hydroxyls are created and transported on the moon, which is a very big question right now. Okay, so here's a mission concept that we can actually learn lots of things about swirls and these other much broader questions in lunar and planetary science. So the goal will be to determine how these swirls form and constrain, at the same time, also the origin of the underlying magnetic anomaly. So what we'd like to do is measure at the surface. So I think Clive was asking about how to measure these things at the surface of the moon. The solar wind flux at the surface, can we correlate the solar wind flux with these dark and light features? Also, the magnetic field variation. How does the magnetic field and how it varies correlate with light and dark features? And can we also measure dust activity at the surface? Okay, so if you want to do all this at the surface and you want to correlate it with these different features over tens of kilometers, you might assume this costs you hundreds of millions of dollars to send a rover there, and it's going to take months to move around. But I think we can do it in only 100 seconds, okay? And we can do it for much less than $100 million. And this mission concept is what we've been working on with UC Santa Cruz, we've been working on with Berkeley and NASA Ames Research Center. The idea is to skim along the surface with you only need a CubeSat, a 3-unit CubeSat, and come down at a very low angle trajectory and make all the measurements you need in about 100 seconds and transmit that data in real time to an orbiting mothership or possibly even directly to the Earth. So you can see as this CubeSat moves through the magnetic anomaly and over the swirl, it can make measurements of the solar wind flux, the magnetic field strength, and as soon as it impacts the surface, the mission's over, we don't learn anything else. But we collected all the data on the way down. And the idea is to collect data below 100 meters is our target goal, which is very close to the surface. We can probably even maybe get tens of meters. And from that, we can take solar wind flux measurements. We can correlate the solar wind flux with albedo features, test the solar wind standoff hypothesis. If we make magnetic field measurements, we can correlate the magnetic field strength and direction with the solar wind flux and with the underlying optical features. We can also make dust measurements and see how if dust is getting lofted just above the surface, down to maybe 100 meters. And we think we can make these critical measurements with 3 probes. Okay. So actually, Ames has done a lot of work in designing some of the mission parts, such as the architecture, the trajectories, the spacecraft. And I'll show you that actually the spacecraft mass can be quite low. We think the cost can be quite low as well. And this would be the first use of CubeSats beyond low Earth orbit. The idea is we'd have an orbiting mothership that launches these CubeSat probes, less than 3 kilograms each, that descend into the moon and make these measurements. Now, how about these CubeSats? You might wonder, is this technology mature or not? But actually, there is a spacecraft that is going to be launching in less than a year from now that Berkeley has been building, and it's an NSF-funded mission. It's called CINEMA, and it's a 3-unit CubeSat, okay? And CINEMA stands for CubeSat for ions, neutrals, electrons, and magnetic fields. It's planned to launch 2012. The idea is this thing actually has a magnetometer with it. It has a particle detector that can be modified to detect the solar wind for this mission, and it's very much underway. And not only does it have a magnetometer, it has a boom. So this is a CubeSat with a boom magnetometer. It also has an inboard one. So there's 2 magnetometers on this, and it can make measurements at the required sensitivity and at the required frequency. And this is all in the order of hundreds of grams of mass. Okay. And this is the Stein Instrument, which is another instrument on the CINEMA spacecraft. And this can be modified slightly to make solar wind measurements for our lunar impactor mission. And you can see, again, the mass of these things is in the order of hundreds of grams, which is compatible with a CubeSat. Berkeley, we have some money from the UARC, which is the Aligned Research Program from the UARC, and they have been providing us with a little bit of money to do these kinds of studies. One of the other things is Berkeley has been designing a dust detector with, again, mass on the order of a few hundred grams, and that can be detect very small dust down to submicron. And so this would be the 3rd instrument on our 3-unit CubeSat. Okay, so I hope you can see, I think swirls are at the intersection of many interesting fields in planetary science. Just look at these, they're interesting geologic features. They also are at the intersection of space weathering, dust transport, water on the moon, and I think a mission of these swirls can really inform a lot of these problems. And interestingly enough, this mission can be done, I think, for low cost, and it's based a lot on existing technologies, and it would be the first CubeSat mission beyond LEO. So I'll take any questions that you have. Thanks. Yep.
Hold on. Do you think maybe instead of having the question of solar wind versus micrometeoroids and space weathering, rephrasing that to micrometeoroids on materials that have been exposed to the solar wind or other ion bombardment or micrometeoroids without any sort of ion bombardment. Because I think everywhere that people have studied space weathering, it's been on materials that are exposed to some sort of ion environment.
Mm-hmm. Yeah, I think that's an interesting point. Sure, I think it's very valid.
Could this be an end of mission target for Artemis, one of the Artemis satellites? They have a high enough data rate to do that before they.
Yeah. Sure. Thank you.
Okay, I guess I do have a question.
Yep.
So how many CubeSats in the mothership? Is it just
Yeah, so it depends on what. So he asked how many CubeSats on the mothership, and it depends on what kind of launch opportunity. I didn't go into too many details about the mission, but one nice thing about this is that there's piggyback launch opportunities on missions like on vehicles that go to GTO. So GTO launches have excess mass capability. So can you design a spacecraft to take advantage of that excess mass capability and has a sufficient number of CubeSats to be launched into the Swirls? And we think 3 is kind of the nominal number of probes we're looking at to accomplish our science and also fit within a package that can piggyback on a GTO launch. Yep.
So just to follow on what I asked Bill Farrell, I was curious. I saw about 350 grams for the equipment. About what's the power usage? What's the power usage associated with that as well? Because with these GLXP landers and rovers, they are required to row for 500 meters, and we can get a traverse across there and take magnetic readings all the way through. So I guess I'm curious about mass and power consumption, which is one of the big things they're primarily concerned about.
The power on what instrument was it that you're curious?
I don't remember exactly.
Okay. Bob, maybe you some more insight.
On